very much, and well, thanks for organizing this nice program. I'm really enjoying it very much so far. Talk on cell motility, but before we come to that, let's maybe mention the people who did most of the work. It's the PhD student doing this. It's Wieland Maat, and he's putting all this stuff together. It's Sebastian Arland, currently postdoc at my institute, and he mainly contributed to the hydrodynamic part of this problem, and Simon Pretorius, another PhD student, he worked mainly on the membrane properties, bending, rigidity, and so on. And then more recently, we also started some collaboration with the group of Jochen Buch. It's an experimental group at the Biotech in Dresden. They just moved from last year from Cambridge to Dresden, and I hope that I come in the end to this as well. Well, and the whole thing is kind of financed by the German Science Foundation. Okay, so cell motility. So I'm interested in describing cells which move around, which swim, or in this case, which crawl. And this is just an example of a well-studied cell type, so-called fish keratocyte, and it's some epithelia cell of a fish. And the nice thing about this cell is that, it moves relatively fast and maintains its morphology, more or less. So let's look at this. So it's we have the cell, and it's moving. So there's clearly some front of the cell and some rear, which are distinguished from each other. So it's moving in one direction, but more or less it maintains the shape. I mean, there are some changes, some fluctuations, but what has been shown for these cells that they more or less move with a stationary shape and move with a constant velocity. So this is kind of what I would like to model, and would like to model with a continuum modeling approach. Now let's step by step go through some requirements which need to be taken into account to describe this. So first of all, I have to describe the cell morphology. So mathematically, it's clearly some moving boundary problem. So this thing moves, it deforms, and so on. So we need to describe the shape of the cell and their movement. Furthermore, there is more fluid inside the cell. So there's some cytosolid actin flow which needs to be modeled, and there's fluid outside in the surroundings. So we have to take this as well into account. And then the cell is surrounded by a membrane, and the membrane has by its own some properties, and we take this into account as well. So there's elastic properties due to bending of the membrane, there's surface tension, and so on. So this so far, just would describe passive things or some cell, but it doesn't so far has any active component or movement. So we need to take this into account as well. And here's some sketch for such a cell and how a cell typically moves. And all cells move more or less by first protruding the cell front and then retracting the cell rear. And this protrusion is mainly done by some actin fibers which polymerize, and these are the small fibers, they polymerize, and by this more or less push against the membrane and thereby deform the membrane and set a direction. So this is going on in this what is called lamellipodium, and there are also some other mechanisms forming this filipodium here, some more needle-like shapes, but however I will not consider this in my model. And then there's the cell rear where we have this stress fibers, and there's some activity due to mysin, and this leads to the retraction force. And there's some active stress generated within the cell by this actin-mysin system. So we need to consider this in some way. And then for the specific cell type I'm interested in here, it's a crawling motion, so I have to take into account also the interaction with the substrate, so there's some adhesion between the cell and the substrate. Okay. So, well, the question is how to incorporate this into our continuum description for the membrane and the flow, and well, we will do this in some more or less effective way, and I come to that. However, so far it's we still need some more, so we kind of need to initiate the polymerization of these actin fibers. We need to tell the cell, well, where is its front and where is its rear. And this is typically done in a cell by, well, some signaling network. So there are various proteins responsible for signaling the, well, formation of actin filaments or their polymerization and so on. And the proteins responsible for this are, well, so-called small GTPases, and they are actually quite well known which type of GTPases are responsible for which. So there are some which bound to the membrane, and there are some which are within the cytosol. And they can attach to the membrane or detach, they diffuse around, and they react with each other. So we can describe such a signaling network by some reaction diffusion system, which takes all that into account. And then we'll use this reaction diffusion system and some instability in there, some diffusional instability, which will set us a polarity for our cell and distinguish between the front and the rear. Okay. And the last thing I would like to take into account is, well, some spatial signal from outside, so that our cell moves in some physiological, meaningful direction, for example, due to chemotaxis, to go into some direction to find, well, nutrients or oxygen or whatever. So I have this external signal and take some chemotaxis here into account. And, well, combined with our signaling network, this actually, well, works in this way to amplify this chemotaxis signal, right? And this will then set the direction for the movement. Okay, so these are the ingredients I would like to take into our mathematical model. Now let's...
Can I ask a quick question?
Sure.
If you have this, why do you also need to know which is your front and which is your back?
Well, the signal might be too small to
so
really...
you want to just have the generic,
right,
cover all cases.
Yeah. Okay, let's go through this step by step and start with the morphology of our cell. Well, classical model to describe the membrane is the spontaneous curvature model going back to Helfrich. And well, the idea is the following. So we have our membrane termed gamma here, the surrounding of our cell, and we have well, bending type energy. H is the mean curvature, H0, or so-called, well, spontaneous curvature, some specific curvature our cell wants to have. And in addition to this, we have surface tension terms, and it's here just written in dimensionless form with some dimensionless parameters, some bending capillary number and a capillary number. So behind this is the bending rigidity and the surface tension. And well, there might be other terms playing a role as well. For example, the Gaussian curvature. However, we here neglect this, and the reason for this is that we, for simplicity, assume that these material parameters are constant, and we are not considering any topological changes. So it's just related to the Euler characteristic and gives the constant to the energy, so we don't need to take this into account for the minimization of the energy. We also assume a spontaneous curvature, but this is also just for simplicity. And then assume in addition that the volume, so our cytosol, the volume of the cytosol is conserved. We here not assume that we have a conserved area, but instead have this surface tension term. So we allow the area to be stretched, or well, one reason for this is might be this stretching due to, well, some endocytosis or exocytosis or something like that. Okay, so that's describing the properties of our membrane, and one could now simply minimize this with this volume conservation and would get some equilibrium shapes for membranes. So this is well studied in the past, and there are nice reviews on that and so on.
Question.
Sure.
So the tension is something that's always tricky in vesicles, membranes, etc. What's your argument for the values you will choose, or that there is actually a tension?
Well, if you most of the models don't have a tension, but you have a Lagrange multiplier then to enforce the area conservation. And in these cells, it seems to be that the area is not really conserved, and there is some stretching and so on going on. And so instead of having this constraint in a Lagrange multiplier, I just have this tension.
Because cells, they have these devious ways of the extra membrane they can dump in, so there are reservoirs.
Yeah, something like this. Okay. So I not just want to minimize this, I want to couple it to the flow. And there's flow inside and outside, so in the cytosol and in the surrounding. And I assume that I can describe this flow by a Newtonian fluid, an incompressible Navier-Stokes equation. So we have
is the flow inside the cell or on the membrane?
Now on the membrane, I neglect any flow on the membrane, so inside the cell and outside. I here don't consider the fluidity of the membrane, so I will talk on this next week, but okay. So it's just a simple model, and for simplicity I also assume that the density and the viscosity are constants, and they're even equal in the two phases. That's probably questionable if that's a good description for the flow, especially in the cytosol, and one could do other things and consider here some stretching or some extraction or compression stresses to account for the actin and myosin activation, and something like this has been done in this work. That's the group of Herbie Lewine and at UCSD, and or one could even have a model for active polar liquid crystal as done by Mike Cates and his co-workers. But in the moment, I'm just happy with my simple description of the flow. So at the membrane, I have to define some boundary conditions for my velocity, and I assume that there's no slip condition, and the velocity is constant, just because I don't know anything better, so I'm not aware of any measurement of slip on a membrane. And the stress, the jump in the stress and normal component, this is just given by the variational derivative of my membrane energy. So that's the bending component and the surface tension component. And then I had this conservation of volume in the cell. That's no longer needed here due to the fact that I have an incompressible flow in the cell. Okay. So this is my simple model. It so far doesn't have any active component, right? So how to incorporate the active component? Well, I do this in some effective way by adding a term, an additional force in this boundary condition. And this additional force acts in normal direction and is proportional to some concentration C1 with some parameter in front. And this C1, it's just the concentration of a membrane-bound GTPases, which signals the formation or the polymerization of these actin fibers. So these actin fibers, as I said, they polymerize and they more or less do this in the direction of the membrane, and they push the membrane, so it's something which really acts on the membrane, and this is the case here as well. So what I assume is that if there's more signaling, then the force will be larger, so it's just an effective way. I'm not considering really any actin fibers there or polymerization. I just say if this formation is signaled, then there will be a force in this direction. Okay.
And this is always pointing out?
That's well, always pointing out here. So if these fibers polymerize, they polarize in the direction to the membrane and push the membrane.
And is it coupled to your chemotactics?
I will come to that here. And well, in the moment, to keep things simple, I neglect any retraction force, but they could be incorporated in a similar way as well. Okay. So what is this C1 and how do we get to have this? Oh, for my, I forget about some adhesion force. So we also consider additional forces due to adhesion just by modifying the flow field in the cytosol and assume that, well, there's some spatial uniform drag force and the adhesion is just proportional to the flow velocity. So the simplest way of doing this, and there are of course more complicated descriptions for doing this, and the detailed way of doing this was described here also in this group of the UCSD, where they used isolated adhesion sites and so on, and spring constants. And however, we do this. And well, then I should mention that all the simulations will be done in a two-dimensional setting, so assuming that my membrane is two-dimensional, which is probably not too bad for the lamellipodium, but it's not so good for the cell real. But that's in the moment what we do. Okay.
So the drag is supposed to model the forces between the
cell and the
network inside the bulk of the cell.
Yeah, with the substrate. So I say that well, the cell and the substrate, they interact, and there's some, well, drag force. Yes. Right, and this is the simplest way of modeling this. Assuming that this is uniform.
So you're not worried about velocity variations in the third dimension?
No, it's just a 2D
Between
model.
the cell is very thin.
Yeah, right, yeah. Right, okay. Now let's come to this signaling network. And as I said, there are this GTPase is responsible for this, and they signal the formation of, well, this lamellipolia, filipolia, actin stress fiber bundles, and so on. They are actually quite well known. And however, in the biology literature, these signaling networks are typically written down as a one-dimensional model, and there are very few exceptions for that. But if one really couple this to some spatial distribution, one finds out that indeed the cell polarity can be established through a coupling of the transport and the signaling pathways, and the polarity can also be maintained by a flux between the cytosol and the membrane. And so one can write down quite complicated signaling networks. However, I here restrict to kind of a minimal reaction diffusion system, which gives me this polarity. And the ingredients I need are, well, some concentration C, which is a GTPase complex, which lives in the cytosol. So it simply diffuses there and attaches to the membrane according to, well, if there's a free site, and there's also some detachment. And then on the membrane, I have two different concentrations. C1 is GTPase concentration, which signals the polymerization of this actin, of these actin fibers, and C2 is some passive component. And they diffuse on the membrane, so that's why I have this Laplace Beltrami operator here, taking account of the curvature terms, and they react with each other by, well, some reaction term with all these reaction coefficients A and B in there. So it's a coupled system of, well, some PDE in a domain, and with a boundary condition which by its own is a set of PDEs on the boundary. So this different dimensionality of the equations here will actually play a role. Now the question is, do we really get some instability out of such a system? And we want to have some diffusion instability or some Turing type instability to give us this polarity. And well, one problem with the Turing type instability is that one typically requires, well, two components, one activator, which however has to diffuse slowly. The activator would be our C1, and one inhibitor, C2, which has to diffuse fast. So these are some requirements to give you this instability. However, there is no reason why this membrane-bound GTPases should diffuse differently, and all the measurements show that well, they at least diffuse within the same order of magnitude, or the diffusion constant is within the same order of magnitude. So this is quite unbiologically to give us an instability. And now comes in the fact that we have, in addition, this concentration C in the cytosol, and one can show that there's even an instability for constant or equal diffusion coefficients D, C1 and DC2, and the only thing I need is that the diffusion in the cytosol has to be faster than on the membrane.
Much
So-
faster, or?
A factor of 100 is fine to get the instability, and this is actually also something which had been measured to be in this order faster in the cytosol. And so, and the instability we get in this regime actually gives us, well, not this typical Turing patterns with many peaks, but just a polarity. And this is, yeah.
Can you somehow comment on the linear effect of this?
Yeah, you could interpret it maybe as a Turing type instability between C1 as the activator and C as the inhibitor, right? And they are coupled due to this attachment-detachment mechanisms on the boundary.
So I mean the difference now between having, for example, just 5 phases.
Mhm.
I mean, what's, because you say it's really different now. Due to the different dimensionality, you have instability that you would not expect.
Right.
So,
And well, I mean, they react with each other, but but they diffuse in the same order. But they are coupled due to this other mechanism. So so in some way, you can still detach from the membrane and diffuse fast through the cytosol and attach on some other place on the membrane. So that's kind of the mechanism which is behind that.
Sorry, so is this an instability for a constant shape of the membrane, or is this an instability?
Yeah, okay, so this linear stability analysis has been done for a spherical constant shape of the membrane. Nothing deforming in the analysis there. And this is done in some recent preprint from Andreas Reetz, former PhD student of mine. He is now in Dortmund with Matthias Rögel. And okay, so, well, luckily, but your point is right. I mean, my shape is not constant and it's not spherical, but luckily the instability survived also for the deforming.
Yeah, actually I was asking a different question, which was whether the instability depended on the shape being able to deform.
Yeah, well,
You know?
I don't know if you can do this for various shapes, but
No, I mean, you could
yeah.
imagine starting with a spherical
Right.
shape plus a small perturbation.
Yeah,
It's just
okay.
one more linear thing.
So we just did this then numerically, and it works out. So
So ultimately, the first equation you could just replace with the Laplacian. So it's an elliptic coupling to
You could-
a parabolic.
yeah, you could do this as well if this is much larger than the other thing. Then.
So it's
Yeah,
it's
yeah.
quasi-static.
right. Okay, so but now, well, your point, all thing deforms and is coupled to the flow. So we have to take this into account into our system. Well, we have well, convection term, u0 was the velocity in our cytosol. So this is simple. But then on the membrane, the terms which need to taken care of here are a bit more involved. So we have movement in tangential direction and in normal direction and stretching and so on. However, this is what you get in order to have conserved, well, C1 and C2. Okay. So in this way, our reaction diffusion system couples to the flow and to the deformation. Okay. Well, models are quite similar to models for like surfactants on droplets or so. Then you have the same type of terms. And well, the last thing I would like to account for was this chemotaxis. Well, just to amplify some spatial signal and set some physiological relevant direction. And again, I do this in some more or less effective way, assuming that my GTPA C1 reacts to this chemoattractant by incorporating this chemotaxis term in this equation. Right? So Xi is the concentration of this chemoattractant, and it goes in the direction of the gradient of this term.
Do you have a thermodynamically consistent way of viewing this? Where you can, because in some way, it's inserting and adding terms as you go, you wonder whether or not you end up maybe violating or not some thermodynamics.
Well, we didn't prove this, but we check like energy decrease in our simulations.
Because this term you had in the boundary condition, the C1N,
yeah.
I was just wondering whether that was a naturally derivable chemical potential.
Well, it's a non-equilibrium term.
Yeah, it's a non-equilibrium. So I supply energy
Equilibrium.
in each time step.
But the same energy for the bulk concentration drives the concentration equation and also can link to variations in energy from varying the surface.
Yeah, it's all coupled together, right? Yeah.
So that's what I'm saying. So if you have a sort of a framework which says, here's my energy, here's my dissipations.
Well, I can at the end show what type of energy terms decrease or don't decrease. Yeah. So this now our complete model, but in
Your chemoattractant, you fix its constant gradient or something?
yeah,
like
it's a
that, or
given.
It's set from the outside.
It's set from the outside. It's given. Yeah. Okay. So how to solve this numerically then? So it's equations on evolving surfaces in the bark, equations which describes the evolution and so on. And a nice way of doing this is using a phase field formulation and using some more or less general description to handle all that. So we have done this over the past years, how to formulate general PDEs on surfaces or in evolving domains with general boundary conditions and so on. And the idea behind this is actually quite simple, and I just gave you the simplest equation one could think of. So think of a Laplacian equation on a surface with a Laplace Beltrami operator here and some scalar valued quantity u, some concentration. Now the way to reformulate this is to more or less go to a variational formulation and then extend it to some larger domain omega. So having gamma, oops. What is gamma? Gamma, and the inside I term omega 1, and then I extend it to some larger domain omega. So omega is everything. And one could do this, or just maybe constantly in normal direction or so. And then, multiply the equation by the surface delta function for gamma, and go back, and then formally you end up with this equation, right? So formally this is probably fine. And now the idea is to smear out this delta function by using a phase field representation. And the way of writing this is phi could be the tanh of the sign distance function to my interface, divided by some scaling factor, and epsilon being a small parameter, giving me the width of the smeared out interface. And then I have some equation in a fixed domain which I can solve.
So you still specify an interface here to define your smoothing function. It's not like the approaches we heard about.
Well, just for this, I could specify this, but the end, it doesn't really have to be this form. So phi could be the solution of some phase field equation to describe the evolution of the interface, and it will be like this. But
Is that what you actually do?
Yeah, that's what I actually do, right? Yeah, and in the same way, you can have like a Laplace equation in this omega 1 with some boundary condition here, just some Neumann boundary condition, and do the same game. So go to a weak formulation, extend it to the whole domain, and then restrict it by some characteristic function or the delta function, and that would be your equation. And one can do this for all types of equations, all types of boundary conditions, and so on. And well, the nice thing is one can actually show, at least by formal matched asymptotics, that if epsilon goes to 0, one indeed converge from this equation back to that, and the convergence actually is second order. And so this is nice. And one can, of course, then also combine the things and actually deal with such problems where one has such things as boundary conditions for these problems. So this is exactly what we want.
And you can also show that the convergence is robust against modifying your model to the phase field, modifying things that will only affect, say, the shape of this tangent function on the scale of epsilon.
Well, it should be like this, but it's kind of, I mean, as long as your phase field model ensures that it's something like this, which you can do, then, well, it's fine, yeah.
So I mean, you know, a typical phase field model is you just take Langdon, Ginsburg, Wilson.
Uh-huh.
Right? But if you took something else, if you put, say, in say, higher order gradients, extra powers of the field, can you show that that doesn't change the results either in the limit of epsilon greater than 0?
Well, phrasing it another way, does your modified phase field models still have this tangent profile, or do you have some variations?
You can
right?
certainly imagine, very easy to make a model that doesn't have a tangent profile.
Yeah, okay. So then you probably have some problem, but in some way it's still, your phase field function will be constant outside of the interface, and it will have some steep gradient in the interface, and the question is how good you use this gradient to approximate your delta function.
Right, I mean, my guess would be that it would converge, and I just wonder
Yeah,
that
but
would work.
okay, but I will not guarantee for second order convergence there. You really need that. Yeah. In some way, it probably will converge. Yeah.
But another question, seeing your sketch, so your geometry is really the interface is like the contact line, right? So it's top view.
Yeah, right.
And you ignore the third dimension
Right.
entirely.
So I just
even when you talk about something being like a surfactant and something being in the bulk, you mean it just diffuses in the contact line, but not on the surface.
Yeah. So it's just a 2D sketch, but you can do this in 3D as well, right? Yeah. Yeah, it's just a 2D picture of my surface, just a line. Yeah. Okay, so this is the approach. And as I said, phi will now not be constructed like this, but phi will be the solution of some phase field function, phase field model to describe the evolution of our membrane. And this is the way to do. So our phi, some order parameter, should be 1 in the cytosol, 0 at the membrane, and -1 in the surrounding. And now a phase field approximation for this bending or spontaneous curvature type energy is this, which, well, more or less without the H0 goes back to conjecture of de Giorgi, and then with this term was first shown by Du to converge to, at least formally, to the previous term. So we just have this Ginsburg-Landau type energy with a gradient term and a double well potential. And what we have here is, well, if you take the variational derivative of this, you end up essentially with this term where your H0 is 0, right? So this then gives you just the mean curvature, an approximation of that. So essentially we again have like the mean curvature minus H0 squared here. So that's the idea behind this. Maybe some mathematical remark here, being the fact that this gives some approximation of the curvature. So if we really would have contact or collision of sharp interfaces, that will explode. And so one needs some relaxation of this, and well, there's some recent work that, well, a natural relaxation does actually not gamma converge to the original energy, and there are some alternative formulations which do come up converge, and there's some recent way of a relatively simple extension, again by Andreas Rietz and some co-workers. However, I will not be concerned with any contact or collision, so this energy will be fine to deal with. Okay. Now, how to incorporate this in my flow problem? Well, I now have my incompressible Navier-Stokes equation in the whole domain and no longer distinguish between the cytosol and the outside. And I have this equation with this additional forcing terms, and these forcing terms are now coming. So this is just the variational derivative of my bending part of the energy and this of the surface tension part of the energy, and it's multiplied by grad phi. Well, grad phi is something which is only non-zero at the membrane, so it's again some force acting on the interface. And then I have this additional active driving part, which was proportional to the concentration C1 and acting in normal direction again, represented here by the gradient term. I have the incompressibility, well, and here I have written out what the variation derivatives are. So G is actually a fourth order term here, and then there are some lower order terms. And then I have to advect my phase field function. So I have this level set type of equation, but now regularized by the variational derivative of my energy. Or phrasing a different way, I have like a convective, well, it's not Cahn-Hilliard, but it's Cahn-Hilliard with lower order terms, right? Equation. Okay.
Well, is the amount of cytosol conserved in this formulation?
Well, okay, good question.
That's not like it.
Yeah, you can, yeah, okay. So, yeah, what we actually do is to conserve this by having an additional Lagrange multiplier to ensure a constant volume in the cytosol. Yeah, okay. So it's not on the slide, so you have an additional term for the Lagrange multiplier in some
You
function.
could conserve it just by putting a Laplacian in the front of the right-hand side.
Yeah, but okay, that's yeah.
I mean, that's the way people normally do it.
Right, but I'm not very much in favor with this approach. Of course, it conserves you the volume, but it changes the dynamics a lot.
But it may change, but it would seem to me that it would change the dynamics in a very physical way. Hydrodynamic behavior of a system with conserved quantity is different than hydrodynamic behavior of a system with unconserved quantity.
Yeah.
That's real physics that you don't want to throw out.
Right, but well, this bending energy actually can be derived from, well, some elastic interactions and so on, and there aren't any additional derivatives in this equation. So to really have the bending type correct, I don't think that it's a good way to, well, have two more derivatives of that.
John suggested won't affect the bending modules that you get.
Yeah, but
Yeah.
I just may throw this in. There is another problem. If you make it conserved, then in equilibrium, the values of phi are not necessarily plus or minus 1. You solve it on a spherical droplet, and you get that inside and outside the droplet there is a shift of the equilibrium properties. Now, if you make all other properties depend on phi, you're in trouble there. So, and that, I mean, that's physical, but if you
But presumably that shift goes to zero with the radius of the droplet.
it's the question, do you interpret phi as a physical quantity or as a marker function?
Yeah.
If you want to interpret it as a characteristic function, a smooth characteristic function, you have to do it this way. You cannot put the Laplace opposite.
But, okay, I mean, yeah. But my point is just that the underlying physics, the long wavelength hydrodynamics of this thing is going to be affected by the fact that cytosol is conserved.
Right.
And if you have a dynamical model that leaves that fact out, you're going to get the long wavelength hydrodynamics wrong.
That's true.
Maybe my suggestion as to how to do it is not a good way to do it, but you have to come up with a way to do it.
Right,
If you want to
but
correct your
we do it
model.
with a Lagrange multiplier to ensure it. Okay.
But that was the reason why I asked about thermodynamic consistency, because in fact what you're suggesting is that if you look at the last equation, you've got a convective Cahn-Hilliard type structure there, which has a known non-thermodynamic feature that you don't select the phases based on the bitangent construction. And so
Yeah.
the other question I was going to ask is that additional term you call it in the Navier-Stokes, to what extent do you know there's no coupling to the order parameter equation?
Why?
So again, you've got this driving
As you
force.
see, yeah, right.
So
Okay.
to what
So
extent
I viewed, okay, so I viewed as phi as just some numerical thing which describes me the characteristic function for the cell, right? And the only reason why this is here is just to regularize this and, well, to ensure that I still have this tangent profile for the phi. Right? And, but the physical meaning of this is, well, it's not really there. Okay, so that's the model. So I have still to couple it to C1, and that's kind of the phase field description for this reaction diffusion model. So we had this equation in the bulk, and as I said, I just extended and multiplied by this characteristic function for the cytosol, and with the boundary condition incorporated that way. And these two equations were the equations on the membrane, and well, I just extended to the whole domain and then multiplied it by this well, approximation for the delta function. So this now gives me a set of systems just in this box omega, and they are all coupled together. And indeed, one can show for this system as well, if one does the matched asymptotics, that it converges to the original reaction diffusion problem. So now we can solve this, and well, the unknown quantities are the velocity, pressure, this phase field variable, and the three concentrations and some auxiliary variables. Well, we do this iteratively, first so for the flow, then for the phase field, then actually for the Lagrange multiplier, sorry to let this out here, and then the concentrations. We use some adaptive mesh refinement to refine along the membrane, and some semi-implicit time stepping. So I don't go into detail. You can ask me if you are interested in. And we do this all in our finite element toolbox Ambis, which allows us to solve this also in parallel and so on. And well, now there are some results. So we start with more or less spherical shape of our cell, and just a constant distribution for C1 and C2 and C, and with some perturbation, so we actually set some direction by perturbing C1. And then what happens indeed is the formation of this instability. So C1 gets a maximum on this side, and the opposite picture can be seen for C2. And C, the concentration in the cytosol, was more or less constant over the time. And then this gives me this active driving force. So this deforms my my cell and well, moves it in this direction. So the cell is moving in this direction and deforms and forms a more or less stationary, well, forms a stationary shape, which moves in with a constant velocity at the end. Okay. So our instability survives also for this deforming interface, and gives me what I actually, well, expected, and these shapes are quite similar to what we have seen at the beginning. And so what we now can do is to, well, vary some of the parameters, well, the bending rigidity, the surface tension, and this active coupling strength in some reasonable parameter regime, and look at the stationary shape, and well, the bending rigidity seems to be not really, or modifications of this not really to affect the shape, however the surface tension does, and this active coupling as well. Well, this is some effective parameter. There are no experimental measurements for that, of course, but all the other ones are in some regime which has been measured for membranes as well. Okay. So now,
Do you always get a stable shape?
no. No, if you set some parameters off from that, then you don't get this. You get oscillations as well. And well, this is just to demonstrate that also the chemotaxis works. So we have, well, just for fun, have a rotating chemotaxis signal, and my cell, well, indeed, then follows this and also rotates, so it's moving along that. And well, the model, even if set up and use parameters for this fish keratocyte, is however quite general, and probably can be used for other cell types as well. And some more recent work with Jochen Guck and his group is on some problems they did a couple of years ago on this myeloid cells, which where they looked at well, tissue infiltration and what's the cell mechanics, how cell mechanics can actually influence this. So what they did is to, well, modify some of these mechanical properties, especially this, the activity of this actin in there, and then looked at like pore entry times for such cells in some small pores. And well, the speculated application for this is that if one really can modify the cell in such a way that this entry time can be or will be reduced, then that might be some well, treatment of diseases where such an increased motility is important, for example, in cancer metastasis. And so we are now interested in how does well, changing the mechanical properties of the cell really influences the possibility of a cell to go into such small channels. And well, this is pretty much work in progress, but there are some first well, semi-quantitative agreements. So this is the cell they have, and there's some chemotaxis signal, so the cell really wants to move into this small channel. It has deformed quite a lot to do this, and well, depending on its mechanical properties, it can do or can't do. And well, this is our simulation. We at least get the same time steps here, and well, the form of the cell doesn't quite look like this. However, it's doing the way, and it's so what we have to, in addition, take into account here is some interaction with the wall and so on, and then, but it essentially, well, deforms and moves into that. Okay, but this is work in progress, and don't have any further results here. So let's conclude here. What I talked on is a, well, consistent continuum model for cell motility, where I coupled mechanics and signaling and considered the hydrodynamics, membrane properties, reaction diffusion mechanism, and chemotaxis. So the membrane, I think, the model, I think, is able to reproduce some characteristic properties for this fish keratocytes. We also get some stationary shape, which looks similar to this cell types, and a constant velocity with where this shape is moving with. Well, and well, more or less the model suggests that one really needs this coupling of this actin polymerization, the adhesion, and the membrane forces. And at the end, we also looked at some confined geometries. Okay, thank you.
Why do you need inertia there in the flow?
Okay, yeah, that's you see the Reynolds number is very small. You don't really need that. Probably you can probably get the same results also
for example, you could just throw inertia out and then.
Yeah, we would probably get the same results also with Stokes from. Yeah.
Related question: if you throw inertia out, you can also throw, if it's sufficiently long length scales, you can throw viscosity out. The drag will dominate the viscosity of the long length scales. And the question I was going to ask you was, what are those length scales? Is the cell comparable to the size where you're crossing over from being viscous dominated to being drag dominated? Or is it a crossover regime, or is viscosity dominating? Or do you have a sense of that?
Well, yeah, good question. So
you said you had calculated the energies of these solutions, so
yeah.
you would also be able to pull out the dissipation rates. So the Stokes dissipation grad U squared friction dissipation u
Yeah.
squared, which one is dominant?
Okay, well, we can go through this. I don't know in the moment, but it's probably in the paper. Yeah.
In the chemotaxis gradient, your cells move along the long axis, but the fish keratocytes, they move along the short axis.
Yeah.
Indeed, movement along the long axis seems to be hydrodynamically much more efficient than how the fish keratocytes actually move.
Right.
But the question is, what's missing in the model to have them move along the short axis?
Okay, so this,
I mean, we're related. You outline the force balance that's going on.
right.
It has to be a pusher or a puller or something.
Okay, that's a specific problem of a changing chemotaxis signal here where the thing rotates. So,
No, in the when it crawls into the channel, it was.
okay. Right, but there doesn't have any other chance than to deform. Otherwise, it wouldn't move into the channel, right?
And have you obtained any solution
Yeah.
where it moves along the,
Yeah.
the short axis?
Yeah, it's in the paper as well. If you have a constant chemotaxis signal, then it probably does this.
Yeah, so the oscillation regime, so you see atoms of oscillating. Is that
Well,
Turing oscillation then, or?
Well, the oscillation
Yes,
regime, we
yes,
also
yes.
got for parameter regimes which are out of the range for which have been measured experimentally. So we don't really.
No, but this is
Consider
back to the
this.
Reynolds number. I mean, in some ways, this taking advantage of inertia
I don't know.
or
Yeah,
Turing.
I don't think that it is a realistic regime.
So you talk about, I mean, the adhesion forces, but if I understand correctly, the only aspect of adhesion you put on is drag.
Yeah.
And so it's actually not making use of adhesion to move the
Yeah.
cells.
Yeah.
Is that
Okay.
right?
Yeah. So it's the simplest way of.
And so this would swim in bulk. Or would it be surface?
Right. Yeah.
Have you looked at ball?
Hmm?
Have you looked at ball?
Well, it's a 2D model.
So I'm asking, have you extended it?
No.
I mean, if you get rid of the friction, then you don't, what's the limiting shape? Then it has to be balanced. The only dissipation mechanism is Stokes dissipation. So then that's a high Reynolds number. No?
It's active.
Okay.
So, can I ask a question about if you just take the reaction diffusion part on its own, that is somehow being pumped somehow. I mean, does that have an intrinsic relaxation time in it, that set of equations just for the reaction diffusion part? In other words, if I just suddenly killed off the cell, how long would it take those chemicals to relax into a state of uniform death? The reason I'm asking is because if you take a keratocyte, you can laser ablate it, you can just chop off the nucleus so that there's no regulatory machinery still working, they'll still move for quite some time.
Okay.
So, and in the end, it will run out. And my question really is whether that's just when the ATP runs out, or whether there's something else.
Yeah. So no, we haven't looked at this. I mean, here I guess we assume that the reservoir of C is large enough, right? So it will never run out.
So the thing is just the way those equations work. As long as I'm keeping C maintained, the rest of it is just going to keep driving. Okay, I see.
Right.
I see. So there's no. So the relaxation time attached to that would be to do with the decay of C, which you're holding constant anyway. So okay, fine.
Yeah.
Sorry, what in this equation holds C constant?
No, it doesn't hold C constant, but it's.
It looks like you're making C disappear as it goes into the.
Sure, but.
But something is supplying C somewhere.
Yeah, you can also detach from the membrane to into C again, but the reservoir for C is much larger than on the membrane. So at least in the time frame I'm looked at, it seems to be that there's always enough C to drive this. It will never run out. But you're of course right. I mean, if I run this forever, there will be some effect.
Okay. The only other question I had about when you do the in-plane diffusion, the thing is that I can see why obviously the lamellipodium is quite flat, so I can see why a quasi two-dimensional picture like that is sensible. However, on the membrane, it might be that the shortest path between one side and the
Would
other is
be
across the top.
yeah, okay, yeah, right.
So it's
that-
not quite
yeah.
right that the diffusion is
right.
in the plane of the
Yeah,
perimeter.
yeah.
Yeah. Okay. So I don't have a suggestion of how to cure that without doing
Yeah.
the three-dimensional.
You're right.
But the elliptic part might be playing that role. I mean, this concentration field C allows communication globally.
So that it may not care whether it's through the cytosol or across
Yeah.
the top of the membrane, for instance. Possibly that's
Yeah,
right.
yeah.
Okay. I see.
But to extend it to 3D, I mean, the equations are, well, they are written here. They will not change, right? So,
I do understand.
yeah.
Time for another question? Rory?
I got a bit confused with, you said at one point that there was no slip at the membrane, but then you were talking about the drag for...
Yeah, so
The
the,
membrane
So-
so the membrane
Are we
is just
talking
this line, right? So,
So there's no
Okay.
pinning
Okay.
type
There's
force
no-
at the perimeter, is what you're
yeah,
saying.
right.
But, right. And then just and in the interior of that though, do you or do you not actually have this depth averaged drag force against the wall? Like you seem to change. You said it. We put it in, and then at some point you said it maybe wasn't important. I couldn't. Can you
Well,
just
it's
repeat what you
2D,
said
so-
about that? No,
Is it strictly 2D?
It's strictly 2D.
Yeah, but in the
yeah.
2D equation, you can have
You have-
a term which is basically is interested
Related
in
to
the
the
absolute
height?
velocity,
You had the
and is a height averaged
Is there-
Oh, I-
viscous drag. But did that stay in the equations, or did you put it in and then leave it out again?
You mean this term?
I think
Well, there was this
This
U0
one?
and that stuff.
Yeah.
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 Now, is that still there at the end, or
Um,
have you eliminated that as well?
Well, the question is where does this would enter in the phase field model? You could
Well, it
well,
would enter there in a term which was
yeah.
a Galilean not invariant. In other words, something which says
Yeah,
that
okay.
U
So
is a
it's-
drag which is proportional to U rather than its gradient.
It's not in there.
Okay.
Yeah, but yeah.
So you mean the simulations you showed us, you actually did not have any drag?
Well, I mean that. Well, so what we did is to have a coefficient in here, right? So which in some way describes similar effects, so that this thing is convected, well, with some drag. Yeah. Yeah. All right.
No,
So.
I mean, the question is whether there's a drag term in the Navier-Stokes equation.
No, there's
I
no
don't see
drag
one.
term. Yeah, there's no drag term. Yeah, right.
Okay, so we should probably give Mike a minute to set up.
Yeah.
So, 1 second.